Okay, so good morning, class. Welcome back. So in this recording, we're going to take a look at section 13.1, which is comparing three or more population means. And then the method that we're going to use, we call this method is the one-way analysis of variance or ANOVA. So ANOVA's or one-way analysis of variance is a technique that we use it to compare three or more population mean. So in section 11.2, we compare two population means. We now extend the concept of comparing two population mean to compare three or more population mean. So we're going to use an analysis of variance. So what is analysis of variance? So analysis of variance or ANOVA is an inferential method used to test the equalities of three or more population mean. So theoretically, you can use in this ANOVA tab to do comparison of three or more population means. But for our class, we only focus on three population means. You're gonna know why. Okay. So ANOVA is an inferential method used to test the equality of three or more population mean. So we're gonna use the same idea for the hypothesis that we have done so far for all of the chapter, right? So it's gonna be similar idea. The procedure of the hypothesis will be the same. So step number 0, we need to double check the requirement. So let's take a look what's gonna be the requirement for the hypothesis test. So requirement for hypothesis testing regarding three or more population mean using one-way ANOVA test. So the first requirement, there are k symbol random sample. So k is going to be some number more than or equal to 3. So there are k symbol random sample, one from each of the k population, or a randomized experiment with k treatment, and k have to be more than or equal to 3. So we're going to compare three or more population mean. So that's why make sure that k is a number that's greater than or equal to 3. So at least going to be 3. So the first requirement, make sure that we have a symbol random sample, right? So we have k different symbol random sample. Now the second requirement that the k samples are independent. So each of the sample that we're using, they need to be independent of each other. That is, the subject in one group cannot be related to in any way to the subject in the second group and then in the other group. The third requirement is the population is normally distributed. So this is going to be the third requirement. The population needs to be normally distributed. Okay. And then the next requirement for this hypothesis test ANOVA is the population have the same variance. So you want to make sure that all of the population have the same variance. That is, each treatment group has a population variance of sigma squared. So you want to make sure that the population have the same variance. So how we're going to double check this condition, how you want to make sure that this condition will be true for this ANOVA test. So we can check this by verifying that the largest sample standard deviation is no more than twice the smallest standard deviation. That's how we check the last condition. The largest sample standard deviation is no more than twice the smallest sample standard deviation. So you might use the one start option on your calculator to calculate the sample standard deviation. And you want to make sure that the largest sample standard deviation is no more than twice the smallest standard deviation. So no more than, which means less than or equal. So the largest standard deviation is less than or equal 2 times the smallest standard deviation. So that's going to be the requirement for the ANOVA test, right? So we have 4 of them. The first one is symbol random sample. Make sure that we have k symbol random sample. K is going to be more than or equal to 3. The second requirement, you want to make sure that the k samples are independent. The third requirement, the population are normally distributed. And then the last requirement, the population have the same variance. So that's going to be the requirement or the condition for the hypothesis test of three or more population mean. So what's the ideas of these ANOVA test or analysis of variance? So the ideas of the ANOVA test, we're going to focus on the case when k is equal 3. Okay. So for the known hypothesis, we're going to assume that the three population means will be equal. So mu1 is equal, mu2 is equal, mu3. So how we're going to state the alternative hypothesis? So this is how we state the alternative hypothesis. So for the alternative hypothesis, we're going to say that at least one of the population means is different from the other. So at least one of the population means is different from the other. So at least one of them will be not the same. So this is the visual explanation of the known hypothesis. All of the population mean will be equal. This is going to be the alternative hypothesis. At least one of the population mean will be different from the other. So now let's give you a quick note before we move on to the procedures of the ANOVA test, right? So if the data gonna take you to reject the known hypothesis, yeah. So if the data lead to reject the known hypothesis, so we reject that the population means will be equal. So we're gonna support the alternative hypothesis, which means that at least one of the population means is different, right? Then we reject the assumption that all of the population means are equal. However, we do not know which or how many are different. So if you're going to support the alternative hypothesis, we can say that at least one of the population means is different from the rest. But you don't know exactly which one is different from the others, and you don't know exactly how many of them will be different from the other. Yeah. So to find this information, you might construct a box plot for each of the lists on the same plot scale to be able to compare them. So in order to determine which population means is different from the rest, you have to use in the box plot to confirm this conclusion. Yeah. So we're gonna use in the box plot that we showed it in the previous section already. So I hope you can remember. If not, we're gonna review this anyway, right? So in order to determine which population means is different from the rest, you're gonna use in the box plot. You're gonna do the 3 box plots on the same coordinates so we can determine which population means is different from the rest. Okay. So that's gonna be the ideas of the ANOVA test. So the known hypothesis, all of the population mean will be equal. The alternative hypothesis, we're gonna say that at least one of the population means is different from the rest. Now let's take a look at the procedure for the ANOVA test then. So step number 1 is done, or step number 0, I'm sorry, yeah. So step number 0 would be double check the condition, right? Okay, so verify the condition or the requirement. So we just talked about the requirements already. Now we're gonna go to step number 1. So for step number 1, we're gonna determine the known and the alternative hypothesis, and then the idea is for the known hypothesis, we're going to assume that mu1 is equal, mu2 is equal, mu3 is equal, mu4, mu5, if you have more than 3, right? So for our class, we only focus on 3s, okay? So mu1 is equal, mu2 is equal, mu3. So we assume that the 3 population means will be equal. For the alternative hypothesis, we're going to say that at least one of the population means is different from the other. So that's how we state the alternative hypothesis. So that's step number 1. Now, step number 2, we're going to do this determine significant level alpha, right? So should be the most easy step in the hypothesis test. So most of the time, alpha should be given in the question. If alpha is not given, then you are the one who controls it. So you might use an alpha is equal 5%, 0.05. So step number 2, determine significant level alpha. Now step number 3, we're going to calculate a test statistic, and we're going to directly use the shortcut for the calculation of the test statistics. Everyone, you don't need to do it by hand, okay? So calculate the test statistic F0 using the calculator function ANOVA. Okay, so there is a function on the calculator that's going to be named as ANOVA. Do not do it by hands. Use a calculator output. Yeah, so this is going to be the formula to calculate a test statistic. Maybe that's not an easy one, right? So that's why we're going to use the ANOVA function from your calculator to get the answer for the test statistic. So this is the procedure. That's how we use an ANOVA to get the answer. Yeah, so you're going to input all of the data onto list number 1, 2, and 3. After that, we're going to go to stats and then test and then select ANOVA. Yeah, so the shortcut we're going to use will be ANOVA, analysis of variance. Yeah, so analysis of variance, ANOVA. Yeah. Okay. And then you just select the list, right? So after you select ANOVA, you just indicate a list. So how many lists we have? So L1, comma, L2, comma, L3. If you have more lists, then comma L4, comma L5, and etc. And then hit the enter key so we can get the answer for the test statistic for step number 3, and then the p-value for step number 4. So for step 3 and 4 of this ANOVA test, we're going to use in the calculator to get the answer there. Okay. Now, after we got the answer for p-value, I hope you can remember step number 5, right? We're going to compare p-values and alpha to get the conclusion, right? So if p-values is less than alpha, we're going to reject the known hypothesis. Yeah, if p-values is less than alpha, we reject the known hypothesis. If p-values is more than alpha, we fail to reject the known hypothesis, or we do not reject the known hypothesis. And then after you got the conclusion of either reject or fail to reject, now we're going to move on to step number 6, which is answer the question of interest in the context. Yeah, so answer the question of interest in the context of the application. Okay, so there is sufficient, there is insufficient evidence. Yeah. So that's going to be the procedure for the ANOVA test. So you might look like pause the recording for a few seconds, review the procedure for the hypothesis before we take a look at the first example then. So we're going to use the same procedure for all of the hypotheses, right? So step number 0, we double check the condition. Step number 1, we just determine the known and the alternative hypothesis. Step number 2, we select the significant level alpha. Step number 3, we calculate the test statistic by using a shortcut or the formula. Step number 4, we're going to use the shortcut to get the answer for p-values. And then step number 5, we compare p-values and alpha to get the conclusion of either reject or fail to reject. If p-values is less than alpha, we reject the known hypothesis. If p-values is more than alpha, we fail to reject the known hypothesis. And then after you got a conclusion of reject or fail to reject, you're going to move on to step number 6, answer the question of interest based on the context of the application, right? So there is sufficient, there is insufficient. Okay. So once again, that's going to be the procedure for the hypothesis test. And then for the ANOVA test, we're going to use a similar idea. But luckily, we're just using the shortcut ANOVA to get the answer for step 3 and step number 4. You don't have to do the calculation for the test statistics. Just input the data onto your calculators. And after that, we're just using ANOVA to get the test statistics and p-values. Okay. Now, we're going to try the first question together then. Okay, so let's take a look at the first practice question of these ANOVA tests. Okay, so the following data represent the weight in terms of gram of randomly selected pennies minted at Denver Mint 2005, 2010, and 2015. So we have 3 different years, right? So 2005, 10, and 15. So test the hypothesis of equal mean. So test the hypothesis of equal mean. So we're going to compare the means, and you want to know if the means are equal. And then we're going to get compare the means of 3 different years. So this is going to be an ANOVA test because we compare 3 or more population means. And we are given alpha is equal 5%. So alpha is equal 5% level of significance. A quick note that the normal probability plus indicate that the population, the sample data come from a normal population. So that's one of the conditions we need to know is, right? So it is a random sample. So we're going to check the condition first, right? Before we actually perform the hypothesis test, which is ANOVA. So it is a random sample. Yes, right? So the following data represent the weight in terms of gram of randomly selected pennies, right? So this is a randomly selected penny. So I'm going to say, oh, this is a random sample. Yes. Are they independent? I'm going to say yes also, because after we select a penny from the year 2005, we have no idea what pennies in 2010 and 2015 will be selected. So they're going to be independent. Is the population normally distributed? I'm going to say yes also, because the normal probability plus indicate that the sample data come from a normal population. So the third population also, the third condition is true. Now, the last condition is the largest standard deviation is no more than twice the smallest standard deviation. It should be yes, right? But how can we know that's yes? So before we can know this if the last condition is yes or no, you have to input the data onto your calculators and get the standard deviation for the 3 different lists. Now, so I'm going to go start, and then I'm going to go to the edit option. I will remove the data that we have earlier for this one. I remove the data for list number 2. I remove the data for list number 3 also. Okay, so now I'm going to change and update the list, right? So that's going to be 2005, 2.5, 2.5 again, 2.49, 2.53, 2.46, 2.5, 2.47, or 47. 2.47, 2.53, 2.51, 2.49, 2.48. Okay. So make sure that we have 11. This is 11, 2, 4, 6, 8, 10, 11. Now I'm going to move on list number 2. So I input the data value for the year 2010. 2.52, 2.54, 2.50, 2.48, 2.52, 2.50, 2.49, 2.53, 2.48, 2.55, and then 2.49. Okay, so that's the second list. Now similar ideas, I'm gonna go to the third list, right? 2.5, 2.48, 2.49, 2.5, 2.48, 2.52, 2.51. Okay, so we just got the answer, the input of L1, L2, L3, right? Now we're gonna use in one bar stat to get the answer, the standard deviation for each of the lists. So we're gonna go stat and then calculate one bar stat. Now I'm gonna do list number 1 first. Okay, so for list number 1, I'm gonna specify that the list is gonna be L1, and then we don't have the frequency list, so leave it blank, and then go down to calculate. Okay. Now the standard deviation for the first list is 0.0220. Okay, so I'm gonna show the answer right here. So I know that the answer for S1, the standard deviation for the first list, 0.0220. Okay. Now similar ideas, I need to find out the standard deviation for the second list, S2. S2. And then similar ideas, I need to find out the standard deviation for the third list, S3. Okay, now we're gonna use the calculators again, now for the second list, right? Now we're gonna go back to stats and then calculate one by stats. Now we're gonna use in the list will be list number 2. And then we don't have the frequency list either. So we go down to calculate. Okay. So the standard deviation is 0.0243, 0.0243, 0.0243. And one more time, the third list right here, right? So we're gonna go stats again, calculate one by stat. And we're gonna do list number 3. So changing the list to L3s, and then we don't have frequency list, calculate. Okay, 0.0125. Okay, so 0.0125. Okay. So now among those 3 standard deviations, you're gonna take the largest one. So the largest one is this one, S2. So S2 is gonna be the largest standard deviation, and the smallest standard deviation will be S3, right? So you want to make sure that the largest standard deviation is no more than twice the smallest standard deviation. Yeah, so the largest standard deviation is less than or equal 2 times the smallest. Yeah, so the largest is which one? So the largest standard deviation is 0.0243. Is that less than or equal 2 times the smallest 0.0125? So 0.0243 is that less than or equal? We're gonna do that multiplication then. So we're gonna do 2 times it by 0.0125. So that's gonna be 0.025. Okay. 0.025. I will add one more decimal place so they have the same number of decimal place so we can easily compare it. So 0.0243 is that less than or equal 0.0250. It's each, right? So which means that the last condition, the fourth condition is true because the largest standard deviation is less than or equal 2 times the smallest standard deviation. Excuse me. So that's gonna be the condition. You want to make sure all of the conditions are good right before we move on to the hypothesis test. Okay. Now step number 1. We're going to state the known and the alternative hypothesis. So after we're done checking the condition, now we're moving on to step number 1. So for the known hypothesis, we're going to say that mu1 is equal, mu2 is equal, mu3. For the alternative hypothesis, we're going to say at least one. Yeah, so at least one of the means is different from the rest. So at least one of the means is different from the other. So that's how we say the known and the alternatives hypothesis. So step number 1 is done. Now step number 2, right? So step number 2, we're gonna do the significant level alpha, right? What's the values of alpha then? So at the alpha is equal 0.05. So alpha is equal 0.05. So step number 2 is done. Okay, so now we're ready for step number 3, right? So for step number 3, we're gonna use the ANOVA test then. So I'm gonna say using ANOVA for list number 1, list number 2, and list number 3 to have the answer for the test statistic F0. Okay, so we're gonna use the shortcut ANOVA, and then the 3 lists that we have, which is L1, L2, L3. Yeah. Okay, so we're gonna use and that's ANOVA test to get the answer for the test statistic F0. Okay, using your ANOVA test then. Okay, so how we accept the ANOVA test? So we're gonna go to the stats option and we're gonna go to the test. And we're gonna go down to the last option, ANOVA. Yeah, so that's gonna be the very last option that we have, which is ANOVA, option H. So ANOVA, okay. So after you select ANOVA, then you should indicate the list. So in this case, we have 3 different lists, L1. So we're gonna go second, key number 1, comma, we have L2. So second, key number 2, comma, we have L3, second, key number 3, and close the parenthesis. Okay. So we're gonna do the ANOVA for list 1, list 2, and list 3. And we just hit the enter keys after that. So we can have the answer for the test statistic then. So the answer for the test statistic will be 1.2703. So 1.2703, that's the answer. 1.0723, that's the answer for the test statistic. And we also have the answer for these p-value, right? So I'm going to shrink it a little bit smaller. Okay. So from the ANOVA output, we got the answer for the test statistic will be 1.2703. And then also from the ANOVA test, we got the answer for p-values is 0.2954. Yeah, so that's going to be the answer for step number 4. We have the answer for p-values 0.2954. Okay, so by using ANOVA test, we got the answer for step number 3 and step number 4. Now, after we got the answer for p-value, we're going to move on to step number 5, compare p-values and alpha to get the conclusion, right? So we're going to compare p-values and alpha to see which one is larger. So p-values equal 0.2954, and then alpha from step number 2, we know that alpha is equal 0.05. So when you're comparing p-values and alpha, which one is more, which one is less? So p-values is actually more than alpha, right? So p-values is greater than alpha. Now, if p-values is greater than alpha, then what is your conclusion then? So what should be your conclusion? Do we reject or fail to reject the known hypothesis? So the rule says that when p-values is less than alpha, we reject. When p-values is more than alpha, we fail to reject the known hypothesis. Yeah. Okay, so because we fail to reject the known hypothesis, which means that the known hypothesis is true. So if the known hypothesis is true, which means that the alternative hypothesis is not true, right? So the alternative hypothesis is not true. So that's why we're going to say there is insufficient evidence. Yeah, so there is insufficient evidence. So there is insufficient evidence to support the claim that the mean weight of the pennies differs in at least one of the population. Yeah. If you want to be more specifically, you can say at 0.05 significant levels. Okay. So that's how we state the conclusion. Yeah. So we fail to reject the known hypothesis, would mean that the known hypothesis is true. That's why we don't have sufficient evidence to say that the means are different. Yeah. Okay. So we fail to reject the known hypothesis, would mean that the known hypothesis is true, which means that the 3 population mean they are still equal, right? So how we can verify this conclusion then? How can we double check if this hypothesis is actually true, which means that the means of the 3 population is still about the same? So in order to verify this final answer, we're gonna use in the box plot that we have earlier. We're gonna do the construction of the 3 box plots on the same coordinate so we can verify the conclusion of this hypothesis test. So I hope that you guys got the idea. You still remember how we accept the box plots, right? So we're gonna go to the start plot right here on top of the key y is equal. That's gonna be the start plot. So in order to accept that option, you have to hit the second key right here. So second y is equal to go to the start plot. And then after you go to the start plots over here, right, you're gonna see that plot number 1 is turned on. So we're gonna go to plot number 1 first. I'm hit the enter key then. Now make sure that you turn on plot number 1. And then in order to select the box plots, make sure that you select option number 4 right here, right? So we go down and go to option number 4 and then hit the enter key to select that. And then the list we're gonna do is list number 1. So we just draw the box plot for list number 1. Now similar idea, we need to do the box plot for list number 2, right? So how we go to plot number 2? You're gonna go on the way to the top again. Instead of selecting plot 1, now we're gonna go to plot number 2 right there. We go to plot number 2 using the arrow key to go to list number 2. Yeah, so just go on the way to the top and then go to the right. So we can access plot number 2 and hit the enter key to select plot number 2. So now at this point, plot number 2 is turn off, right? So you have to turn on plot number 2. So go to the on option, hit the enter key so you can highlight that option. So now it's turned on. For the type, you're gonna use an option number 4 also for the box plots, and then the X list is gonna be list number 2. So we just got the second box plot for list number 2, right? Now similar idea, we go on the way to the top again. Now we're gonna go to plot number 3 to do the third plot. Hit the enter key to select plot number 3. Make sure that you turn on plot number 3. Hit the enter key to highlight option on. For the box plots, for the type, we're gonna use in the box plots option number 4. And then for the X list, we're gonna go list number 3. Okay. So plot number 1, we're gonna use in the data for list number 1. Plot number 2, we're gonna use in the data for list number 2. And then plot number 3, we're using the data for list number 3. So we're gonna do the 3 box plots on the same coordinate so we can verify if the hypothesis conclusion is true. Yeah. Now after we're done with the plot, now we're gonna go to the zoom option right here. That can be zoom, and then we're gonna go to option number 9, zoom start. We're gonna go down to option number 9, zoom start, and hit the enter key. There we go. Oh, I got something extra. I will go back and clear it. Okay, I will clear this one. Now, once again, after you got the 3 plots, we're gonna go zoom and option number 9. Okay, so now we have the 3 box plots on the same coordinate, right? And then based on this plots over here, you can see that the mean right here, the middle line is almost perfectly lines up, right? So this is the mean for the first one. This is the mean for the second one. This is the mean for the third one. Look like all of them have the same mean. So that's why we fail to reject the known hypothesis, which means that the known hypothesis of equal means still true. Yeah. So this is gonna be the box plots. I will drag the picture over here so you guys can take a look at that later on. Okay. Okay, so this is how we verify the conclusion of the ANOVA test, right? So we're just using the box plot. We're gonna do the box plot for the 3 lists. So for our class, we can only do 3 plots because the calculator that we use it only have plots 1, 2, and 3. So that's why we only limited to the 3 population. But on theory, you can use in this hypothesis test to test 3 or more population mean. Yeah. Okay, so that's gonna be these ANOVA tests, right? So this is the first examples of the ANOVA test. Okay, so now we're gonna try one more practice questions. Yeah. Okay, second practice questions, everyone, for the ANOVA test then. Okay. So the world champion pumpkin chunking contest is held at every falls in Delaware, right? Contestant will build a device to move these 8 to 10 pound pumpkin across a field. The following data represent a simple random sample. Okay, so we have a simple random sample of distances. That pumpkin travels in terms of feet in the 3 different years. So there's going to be 3 different years. It is evident to conclude that the mean distance that a pumpkin travel differ for the various years. So can we say that the mean distance that a pumpkin travels differ for each of the years? At alpha is equal 5% significant level. A normal probability plus indicate that the sample data come from normal population. Yeah. Okay, so you want to test if the means are different, right? And now we're gonna get the mean for 3 different years, right? It's gonna be 3 different years. So year 1, year 2, year 3. So before we're gonna go any further, we're gonna input the data first, right? Now we're gonna go stats again, edit. I will remove in L3. I will remove an L2. I will remove an L1. Okay, now I will input the data for L1. 4224, 4066, 3980 or 68. 3968, 3596, 37, 39, sorry. 3970, 3877, 4224, 4066, 3968, 3596, 3970, okay, 3877. Now 3871, 3579, 3623, 3275, 3022, 3632. 3490, 3416, 4211, 3238, 3579, 3552. Okay, so we got the distance that the pumpkin travel in the 3 different years, right? So we just got the distance into list 1, 2, and 3. Okay. Okay, so this is gonna be the comparison of 3 or more population means. So we're gonna use an ANOVA. So before we can use an ANOVA, let's double check the condition. So the first condition, which means that it is a simple random sample. I'm gonna say yes, right? So a simple random samples of distances. So this is a yes. Now, are they independent? Yeah, so the pumpkin for year 1, year 2, and year 3, they're gonna be independent. They are not related in any ways, right? So the sample that we have gonna be independent. Either population normally distributed, we have that also. Normal probability plus indicate that the sample data come from a normal population. So the third condition is yes also. Now the last condition, the largest standard deviation is no more than twice the smallest sample standard deviation. So I'm gonna double check that condition before we do the ANOVA test. So in order to double check that condition, I need to find out the 3 standard deviation or the 3 sample standard deviation S1, S2, S3. Okay, so in order to find out those 3 sample standard deviation, I'm gonna go back to the one bar stat. I'm gonna do the one bar stat for the 3 list so we can get the 3 standard deviation. Okay. So after we got L1, L2, L3, now we're gonna go to stat and then we're gonna go to the calculation option and we're gonna go one bar stat. And then I'm gonna do list number 1 first. Okay, I'm gonna change in the list to list number 1. We don't have the frequency list, leave it blank. Okay, calculate. So the first standard deviation is 209.7145. 209.7145. So 209.7145. Oh. Okay, so that's going to be the first sample standard deviation, 209.7145. Now, similar ideas, I'm going to do one bar start for the second list. So we're going to go stats, and then we're going to go calculate one bar start. Now the list is going to be list number 2, second L2. Okay, 301, 8421. So 301, 301, 8421. Okay, now similar idea for the third list. So we go stats and then calculate one bar start. Now the list is going to be L3. Okay, 331, 93, 37, 331, 93, 37. Okay, so we got the 3 sample standard deviation. Now you want to make sure that the largest of them gonna be less than or equal to 2 times the smallest. So the largest one is gonna be the 331. You want to make sure that the largest standard deviation is less than or equal 2 times the smallest, 2 times the smallest, and the smallest is going to be look like the 209. Okay, so I think this condition should be okay, right? Because we have there's a 331. And then we're going to do 2 times that. Yeah, so it's going to be 2 times it by 209.7145. That's going to be 419, 429, 419. So 331 is actually less than 419, right? So this condition should be okay. Yeah. So the third condition, the last condition, are good. Okay, so which means I'm going to say yes for the last condition. Okay, so all of the condition, all of the requirement has been checked and they are good, right? So now we can move on and do the hypothesis test. Yeah, so we can move on and do the hypothesis test then. Okay. So for the known hypothesis, we're going to determine the known and the alternative hypothesis, right? So we're going to compare 3 population mean. So for the known hypothesis, we're going to say that the means will be equal. So mu1 is equal mu2 is equal mu3. For the alternative hypothesis, we're going to say what? What how we say the alternative hypothesis? We're going to say that at least, right? So at least one. Yeah, so at least one of the means is different from the other. So at least one of the means is different from the other. So that's how we say the known and the alternative hypothesis. Now, step number 1 is done. Now we're ready for step number 2. So step number 2, we do the significant level alpha, right? So just select the significant level alpha based on the seriousness of McIntyre number 1 error. Yeah. So alpha will be equal 5%, right? Alpha is equal 5%, 0.05. Okay, so step number 2 is done. Okay, so far so good. Okay, so now we're gonna move it on to step number 3. So for step number 3, we're gonna use the shortcut, right? So I'm gonna say using ANOVA for list number 1, list number 2, list number 3 to have the answer for the test statistic F0. Okay. So the shortcut we're using this is gonna be ANOVAs, and then we have the 3 lists, right? So L1, L2, L3. Yeah. So we have the 3 lists, L1, L2, and L3. Okay, so now we're gonna go stat, and we're gonna go to the test option, and you're gonna go down to the last option, ANOVA test. Yeah, so the last option, option H, ANOVA. And then for this case, we're gonna compare 3 different years. So we're gonna indicate, so second key number 1, list 1, second key number 2, list 2, comma, second key number 3 for list number 3. And you might close the parenthesis. Yeah. Okay, so this is gonna be the answer for the test statistic from your calculator ANOVA test, right? So 4.2116, 4.2116. So that's gonna be 4.2116. And I will show the answers of that also, just in case we need it. Okay, so from the ANOVA output, we got the answer for the test statistic is 4.2116. We also have the answer for p-value, right? So let me show the answer for p-values also. So p-value is equal 0.0351, 0.0351. Okay. So using the ANOVA test, we just have the answer for step number 3 and step number 4. So after we got the answer for step number 4, we see p-value. Now we are ready to complete step number 5, right? So for step number 5, we compare p-value 0.0351. And then alpha from step number 2, we know alpha from step number 2 is equal 0.05. So p-value is equal 0.0351 and alpha is equal 0.05. So p-value is less or more. So p-value is actually less than alpha, right? So 0.03 is actually less than 0.05. So p-value is less than alpha. What's your conclusion then? So when we have p-value is less than alpha, we're gonna say what? So we're gonna reject the known hypothesis, right? So we're gonna reject the known hypothesis. Yeah. Hypothesis, yeah, hypothesis, yeah. Okay, so p-value is less than alpha, so we're gonna reject the known hypothesis. So after we reject the known hypothesis, then what we're gonna do then? What's your final conclusion? What's your final answer based on the context of this application then? So because we reject the known hypothesis, would mean that the known hypothesis is not true, right? So if the known hypothesis is not true, which means that the alternative hypothesis is true, right? So which means that we have sufficient evidence, yeah. So there is sufficient to conclude that at least one of the means is different from the rest. Yeah. So or you can copy that. Yeah. To conclude that the mean distance that a pumpkin travel differ for various years at. Yeah. So I'm just gonna copy just that claim. Okay, so we have sufficient evidence to say that that the mean distance that a pumpkin travels differ for various years. Yeah, so for various years. Okay, so that's going to be your conclusion for the hypothesis. So based on this example, the final conclusion say that we have sufficient evidence to say that at least one of the year will have different mean distances than the other years, right? Now, how can we know which year is going to be have the different mean then? So how can we figure out which year does have the different mean then? So we're going to use the box plots again. Okay, so we're going to use the box plot to determine which years will have the different mean than the other years. Okay. So in order to use the box plots one more time, right? So make sure that you have the data first, right? So we're gonna go start, edit, and making sure that we have the three lists for the three different data, right? So we have the three lists for the three different data. Now after you got that, now we're gonna go second, y is equal to accept the start plot. We're gonna do plot number one. Okay, so enter to select plot number one. Make sure that you turn on plot number one, and then for the type, you make sure that you select the box plot. And then for the list, gonna be list number one. And make sure that plot number one is turned on, and you're gonna use in the list number one. Now we're gonna go all the way to the top, and then we're gonna jump over to plot number two, and then hit the enter key to make sure that plot number two is turned on. And then for the types, it's gonna be these box plot. And then for the list, gonna be list number two. Okay. And now we're gonna go move over to the top again. Now go to plot number three and double check. Make sure that plot number three is turned on. And then for the type, we're gonna use in plot number option number 4. And then for the list, we're gonna use in list number 3. Okay, so for list number 3. Now everything's good. Now we're gonna go to zoom, and then we're gonna go to option number 9, zoom stats or zoom statistics. Then hit the enter key. Okay, there you go. Look like we have one outlier. Okay, so look like we have one outlier right there, right? Okay, so this is gonna be the box plot. So we can say that look like the blue one, which is the first year, we have the mean distance different from the other two. Yeah. So the other two is might be different, but it look like they close enough right here, right? So for the second and the third years, even though that the means might be different, but it's not that much. It's not really significant. But for the first year, the means right here is very significantly different with the other 2 years. So based on the box plots, we can just determine that which years we have different mean than the other. So in this case, we can say that year number 1 have the different mean than the other 2 years. Yeah. So that's how we're gonna do the ANOVA test, right? So we're gonna use the box plot to determine which population means will be different from the other. Yeah. So that's how we determine which population means will be different from the others. Yeah. So this is going to be the second example for the box plots. I hope that's going to give you the ideas how we complete the ANOVA test. So the ANOVA test, or one-way ANOVA, or analysis of variance, is an inferential statistic that we use it to compare 3 or more population means. So this is the second example. I think that's good. Now you might, I will stop the sharing at this point. So this is going to be the conclusion of the hypothesis test to compare 3 or more population mean using ANOVA test, analysis of variance. I will stop the recording at this point. I will see you next time.